Welcome, curious minds, to another special deep dive. So this particular deep dive is part of our CSWIP 3.1 exam prep series. It's specifically designed to, sharpen your understanding.
Yeah.
And get you ready for the kinds of multi-choice questions you'll definitely encounter in the welding inspector exam.
Yeah, the format they use.
Exactly. And our goal isn't just about memorizing the right answer. It's deeper than that.
It has to be.
We want you to truly understand the underlying concepts, the why behind the whats, so you can confidently approach any similar question, however it's phrased, and actually apply that knowledge out in the field.
And that deep understanding, that's precisely what elevates a good inspector to, well, an excellent one. The areas we're going to explore today, welding imperfections and fillet weld geometry, they are just fundamental.
The basics, really.
Yeah, the absolute bedrock of ensuring weld quality, structural integrity, and, ultimately public safety. Mastering these concepts means you can not only spot the issues, but also understand where they came from and predict their impact.
That's where the real power lies, isn't it?
Yeah.
Okay, so let's start our exploration. Let's zoom in on some of those tiny culprits that can undermine huge structures.
Yeah.
Welding imperfection.
These are the flaws.
The flaws, the deviations from perfection that inspectors like you are trained to spot. So let's kick off with our first question. Listener, have a think about this one. Which of the following is a planar imperfection? Is it A, lack of sidewall fusion, B, slide inclusion, C, linear porosity, or D, root concavity? Okay, take a moment. Try and visualize those options. What does planar really mean in this context?
Right, that term planar is absolutely critical here. It's key because it describes the two-dimensional nature of the defect, often flat, sort of sheet-like.
Like a plane. Basically.
Exactly. Unlike, say, a volumetric flaw, which might be more rounded or irregular in shape, a planar defect is like a thin crack or maybe an unbonded interface. And these types of imperfections, they're generally seen as far more critical.
Why is that?
Because they act as severe stress concentrators. They can propagate, grow really easily, leading potentially to sudden brittle failure under load.
Ah, okay. That makes sense.
So given that definition, the correct answer here is A, lack of sidewall fusion.
Lack of sidewall fusion. Can you break that down a bit more?
Sure. Lack of sidewall fusion happens when the molten weld metal, it just hasn't properly melted and fused with the base metal right along the side of the joint. Imagine trying to glue two heavy books together, spine to spine.
Okay.
And you miss applying glue along a thin vertical strip right on one of the spines.
Right, I can picture that.
That creates a flat, unbonded plane. If you were to cut through the weld, it often looks like a sharp, straight line. It's like this tiny internal unbonded surface.
Okay. And the others, why aren't they planar?
Well, let's contrast it. A slag inclusion, that's a trapped piece of non-metallic stuff, usually volumetric, irregular shape.
Right.
Linear porosity, that's a series of small, separate gas bubbles. Even if they line up, there's still individual volumetric voids, little bubbles.
Got it.
And root concavity, while it can be serious, it's a surface depression at the weld root. It's not that sharp internal planar discontinuity we talked about. The real difference is their geometry and how they interact with stress. Planar defects are uniquely dangerous because their sharp, crack-like nature really concentrates stress at the tip.
That book analogy really helps visualize it. So it's not just knowing what it is, but understanding its basic shape and the impact of that shape.
Precisely.
Knowing lack of sidewall fusion as planar immediately flags it as, well, a particularly high-risk defect. Okay, this brings us neatly to a crucial follow-up question then. With reference to lack of sidewall fusion, how could this defect be caused? What's the likely reason? Is it A, amperage too high, B, voltage too high, C, amperage too low, or D, gas flow rate too low? Okay, think about the actual welding process. What parameter would directly stop that proper melting and joining at those critical edges?
Well, the root cause for lack of sidewall fusion is actually quite direct. It's about heat. Specifically, insufficient heat input into the sidewall of the joint. You just need enough heat to melt the base metal properly and allow the weld metal to wet it and fuse with it. So thinking about heat, the correct answer has to be C. Amperage too low.
Amperage too low. Okay.
Yeah, amperage directly controls the amount of heat generated at the arc. If your amperage is too low, there simply isn't enough energy, not enough juice, to properly melt those sidewalls, and that leads to a failure to fuse, even if you're depositing the filler metal correctly. It's like trying to boil water on a stove that's just barely warm.
Okay, that makes perfect sense.
Yeah.
What about the other options then?
Well, let's see. If the amperage were too high, you'd probably see different issues like excessive penetration maybe, or undercut, even burn through. Very different problems.
Okay.
Voltage. That mainly influences the arc length and the overall bead profile. Too high a voltage might give you a wider, flatter bead perhaps, or maybe excessive spatter, but typically not lack of sidewall fusion as the main defect.
And gas flow.
Gas flow rate too low. That would likely lead to atmospheric contamination of the molten weld pool. You'd get defects like porosity, maybe oxidation. You see, each parameter tends to have a distinct and predictable impact. Understanding that specific cause and effect is vital.
For inspectors diagnosing problems, sure, but also for welders trying to prevent them in the first place.
Exactly. Both sides of the coin.
That's where the real-world application clicks in, doesn't it? It's not just identifying the flaw, but understanding the why. If you know lack of sidewall fusion often comes from low amps, it gives you a practical path. Prevention, troubleshooting.
It helps develop that inspector's eye.
Right. The ability to not just see what's wrong, but to figure out its origins. Okay. So we've tackled some of those invisible enemies inside the weld. But what about the weld's outward appearance, its shape? That holds vital clues too, right?
Absolutely. Geometry is critical.
Which brings us to another area needing absolute precision.
Yeah.
Understanding fillet weld measurements and geometry. Let's look at a scenario that comes up a lot. A fillet weld has an actual throat thickness of 8 millimeters and a leg length of 7 millimeter. What is the excess weld metal? Your options are A, 2.1 millimeter, B, 1.8 millimeter, 3.1 millimeter, or D, 1.4 millimeter. Now, this one involves a specific definition of excess weld metal, particularly in the context of welding standards. It needs a bit of calculation based on those definitions.
Yes, this is where precise terminology really counts. For fillet weld, okay, the leg length is the distance from the root of the weld out to the toe on the fusion face.
Got it.
And the actual throat thickness is the shortest distance from the face of the weld down to the root.
Okay.
Now, excess weld metal. That refers to the amount of weld material that extends beyond the theoretical throat thickness.
The theoretical throat. How do we figure that out?
Right. The theoretical throat thickness for what we call an ideal miter fillet weld, that's one with a perfectly flat face and equal legs, ideally, is typically calculated by multiplying the leg length by 0.707. It's a standard geometric relationship.
Okay, so 7 millimeter leg length times 0.707.
Exactly. So for a 7 millimeter leg, the theoretical throat would be 7 times 0.707, which is about 4.949 millimeter. Let's call it 4.95 millimeter. That's the ideal amount of metal for that leg size.
Right.
But you measured your actual throat as 8 millimeter. So the difference, the excess would seem to be 8 millimeter minus 4.95 millimeter, which is 3.05 millimeter.
Okay, so about 3.1 millimeter, which is option C, which leads perfectly into our next question, building directly on this. Let's stick with that scenario. With reference to the previous question and the concept of excess weld metal, if this excess weld metal was removed, what would the fillet be? Would it be A, concave fillet weld, B, convex fillet weld, C, miter, or D, undersized fillet weld? Okay, now you need to visualize what happens to that weld profile when you take away that excess material. What shape are you aiming for?
Right. So if you're removing excess weld metal, it strongly implies the weld was initially overfilled. It probably had a convex profile.
Bulging outwards.
Exactly. Its face bulged outwards. The whole point of removing this excess is usually to achieve a specific ideal profile. And in the context of fillet welds, the standard, most efficient, and often the desired shape is the miter profile. So the answer is C. Miter.
Miter. Okay, define that for us again.
A miter fillet weld is one where the weld face is essentially flat or straight. It forms roughly a 45-degree angle to the fusion faces, assuming you have equal leg lengths. It represents the most efficient use of weld metal for a given leg length. It's not overfilled like convex, and it's not underfilled like concave.
The Goldilocks weld.
Kind of, yeah. The just right profile, structurally speaking. So if you started with that 8 millimeter actual throat on a 7 millimeter leg weld that's significantly overfilled, almost certainly convex, by removing the excess metal, you'd be trimming that profile back to achieve that ideal balanced miter shape.
Makes sense.
A concave fillet, conversely, looks caved in, usually due to not enough filler metal. And an undersized fillet just doesn't meet the required dimensions. Removing excess from an overfilled weld wouldn't result in either of those, assuming the leg lengths themselves are correct.
This really hammers home the importance of precise terms and, importantly, visual understanding in weld inspection.
Absolutely.
You're not just looking at a number on a gauge, you're interpreting that number to understand the physical shape, the quality of that weld. Being able to visualize the geometry in your mind's eye.
That's the skill.
And that brings us towards the close of this particular deep dive. We've covered some, well, absolutely crucial ground today, haven't we?
We have indeed.
Distinguishing between planar and other types of welding imperfections, understanding their specific causes, and then diving into the intricate world of fillet weld geometry and those specific measurement calculations, particularly around excess weld metal and what makes an ideal miter profile. Grasping these details, not just memorizing them, but really grasping them, is absolutely vital for success in the CSWIP 3.1 exam.
And beyond the exam, of course.
Oh, absolutely. More importantly, for real-world application as a skilled welding inspector out there on the job.
Indeed. And maybe, as you continue your own deep dive into this challenging but definitely rewarding field, I'd encourage you, the listener, to ponder this. Think about how seemingly small numerical differences or subtle definitions in these standards, how they can translate into really significant differences in the integrity and ultimately the safety of a welded structure.
That's a great point. So keep reviewing these concepts, keep visualizing those welds in your head, and keep asking those important why questions. You're definitely well on your way to mastering the art and the science of welding inspection. Until next time, keep digging deeper.